Hello, Kennedy. Hello, Spencer. Let's see who else is here. Hello, Connor. And hello, Jared, and hello, Zane. So today is the last didactic meeting, and we will meet, except today, I think 4 times more. The Wednesday will be instructions what to write in the report. Wednesday night, it will be like a help session for completing projects. Friday, there will be peer review. I will ask you to send reports by Thursday night, and then we'll do it probably through Google Docs. And then whenever is scheduled exam time, or if we all agree and vote, change it a little bit, you will do presentations. What about today's meeting? The last meeting, there were some comments with Jared's dedicated client. Today, the dedicated client is Zane and Spencer. So the problems you are involved in goes above, in general, 3rd year p-chem. And when you will be explaining what you're doing, still there are some criteria that I will explain on Wednesday. Like if you describe scientific problem, you need to write down Hamiltonian. And it is a little crazy system because it is 2 types of degrees of freedom, electronic and nuclear, and they coexist, which is quite common, like all molecules have both electrons and nuclei. But in our simplified course, we were trying to avoid double or triple variables. So it will be a first step. Another value of today's meeting, so the subject, if I want to summarize it in like 2 words, 3 words, it will be Franck-Condon factors. So when a molecule is irradiated by light of the visible frequency, there is a promotion of electron from home to home, right? And upon such promotion, it absorbs at certain wavelengths, at certain transition energy. And then after it happens something inside, it emits back, right? There is absorption and emission. And there is an experimental fact that in vast majority of objects, emission happens at different wavelengths than absorption. Are you aware of this? Can you tell a few words?
If a molecule is irradiated with UV light, and then it will fluoresce, not in the UV spectrum, but in the visible light spectrum.
Is there a name for this effect?
Is it phosphorescence?
Well, it is when you intentionally excite higher up. But even if you look for lowest available absorption transition, still it will emit at even lower. And the name is Stokes shift between absorption and emission wavelengths. The nature of this effect is that we do have transition energy for electronic, like homologous, but in addition, there are vibrational sublevels. And depending on their match, absorption and emission happens from different pairs of vibrational sublevels. So I'll provide more general concepts and math in support of this. As a little analogy to what we did before in the class, when we were in transition from rigid rotator to spin, we were discussing rotational vibrational spectrum. When molecule is like gas phase molecule, diatomic, is irradiated by light in radio frequency. Well, it's not light, it's electromagnetic radiation. And then there are very low transition energy frequencies, but they involve both oscillatory levels and vibrational levels. So 2 types of degrees of freedom. Same as there, today we will, and the spectra we're looking like wings of an eagle. So today we will make something similar, but instead of vibrational and rotational, it will be vibrational and electronic transitions. And it will be also some substructure of levels. Okay. Hope I said the right one. Yes. So my goal is to arrive to this figure. And basically, if all notations are clear here, then you can surprise me and stand up with the room and slam the door. So what do you see here? Can you just tell a story like what is observed on this image? Like there are two panels.
It looks like a, is that a UV or IR on the left?
Okay, and what is on the right?
Marcus theory type deal? Or is that a polaron state thing?
Okay, and if you if you are not aware of Marcus and polaron, you just have a background of the class. Like if you look on the bottom of the blue line and the structures here, what are they?
States?
States of what?
Energy?
For which system?
Yeah.
For harmonic what? Okay.
Harmonic oscillator?
Yes. So eigenstates of harmonic oscillator, and there are two oscillators, right? And each of them, like blue has blue states, red has red states, and then they overlap somewhere. And then, how do you interpret the notations here?
Ground state and then different eigenvalues.
Of vibrational states.
Yeah.
Right? Oscillator states. And here, excited in different vibrational states. Now, if we assume that the system is perturbed by light of certain frequency, then there could be transitions between these pairs of states, between the states, like from this one to this one, right? Then transition is labeled by 4 indices, like G0, E0. Let's look here. G0, E0, right? And here is the intensity of transition, and here is the transition energy. So this image shows the absorption spectrum for this polaric system. It will be absorption in the infrared from like the transition in the infrared range, but we are looking from G0 to different red states. From G0 to E0, from G0 to E1, from G0 to E2, from G0 to E3, right? So they will have different offsets, different energy transitions, because it is as much here, as much there, as much there. So the energy is ramping up by the fundamental frequency of the oscillator. In addition, the intensity of each transition is different. So it increases first and then decreases. And I realize very much that if you do not do enough homeworks and exams, then most of information will be washed immediately. But there is a little take-home message that you may keep. There is a chance that you will keep it for a longer time. Why intensities of these transitions are different? why there is the transition from 0 to 0 when it is basically resonance between electronic states is not the most intensive.
Because maybe it's not the most stable.
Okay. Well, I would argue because eigenstates, in absence of electric field, they all are stable. But I like the idea. Then the intensity of higher energy transitions will be lower because the higher the energy, less stable. And then it will grow, and the lowest will be still most intense. Other ideas?
Distance travel, maybe?
Okay. I like this idea. I will try to believe Jared and try to develop from his insight. So if there is a probability for interatomic distance to be at this value, if you do electronic transition and if you go to the lowest state of the red parabola, it means that when electrons are jumping from one electronic state to another, nucleus must move, the bond must immediately contract. But it is kind of against conservation of something, conservation of energy, conservation of probability, so it must instantaneously move, which is not very reasonable, right? Therefore, this transition is not as probable, right? But when let's look on the one that is highest intensity, G0 E2, then we are going from this parabola to this structure with 3 hump cannon. And there is a probability that it will be delivered immediately to the rightmost hump. So there will be no unnatural travel of interatomic distance to some strange distances, right? Therefore, there is nothing unnatural and it will be most intense. So I'm going to try my drawing skills. So we are going from here to this. Right? And quantitative measure of lack of the travel to an unnatural positions is the overlap of this wave functions. If we before I was trying to deliver an idea that good eigenstates must be orthonormal. If it is the same eigenstate, their scalar product is 1. If they're different, it will be 0. But here we have two sets of basis states, oscillator 1, oscillator 2. And there is no requirement to have orthonormality between them. So multiplication of this state by any from here will be neither 0 nor 1. It will be somewhere in between. And the one where scalar product of this black thing with this black thing is maximum, then transition is most probable. So when the scalar product of these wave functions is bigger, right? And if you look further, then for higher states, the relative height of the peaks is less and less, and it will be less and less probable to make exact match. And then the intensity will decrease, right? So this concept is called Franck-Condon factors or Franck-Condon overlaps. So these two guys draw this parabolas, basically, or more complicated things. And the word is overlap, which means scalar product of two wave functions. If it is maximal, the optical transition is maximal. If they do not overlap substantially, the transition will be suppressed. So optical transitions, depending on match between vibrational states in initial and final substates in the electronic states, depending on the match of this set of numbers and this set of numbers, the transition will be more and or less intense. Okay, so I believe it is something that you can remember later on. Now I'm starting the stuff that you will forget in 5 minutes after finishing the meeting. So generally, ground and excited states are not parabolas, but more complicated potentials. But we are looking on them near equilibrium when they behave like parabolas. If you want to describe molecular system rigorously, as we were trying to do during this 3 months in a class, one needs to set up Hamiltonian and then solve Schrödinger equation, either time dependent, time independent. Right? So Hamiltonian will include everything related to electrons, electronic, nuclear repulsion, and kinetic energy of nucleus. Right? And the wave function will depend on both positions of electrons and positions of nuclei. And even if there is only one electron, one nucleus, like H2+, still it is quite complicated system. In all realistic molecules, it is over the head for pen and paper solutions. Therefore, one practices computational chemistry. That is all next semester. So wave function, which is quite complicated, but even if there is one nucleus and one electron, here's eigenenergy. So there is a so-called Born-Oppenheimer approximation that tells the previous equation that has all terms of energy related to electrons and all terms of energy related to nucleus separated from one Schrödinger equation to two Schrödinger equations. And it is possible only in certain limits. So everything related to electrons defines wave function for electrons. And you can put index if there are several. And everything related to nuclear kinetic energy, repulsion, and contribution from interaction with electrons into Schrödinger equation for nuclear wave function, like the one we did for harmonic oscillator. So they need to be considered together for realistic movement, and not precise. Oh, sorry. I'm just going to move this. Okay. So, and under this so-called Born-Oppenheimer approximation, the wave function for the whole molecule can be represented in form of products between electronic wave function and nuclear wave function. So it is a big statement that one can separate variables and deal with electrons and nucleus, same as we were doing with transversal motions in 2- and 3-dimensional particle in the box. But it is possible in certain limits, especially when temperature is low, reactions are not going on, system is close to equilibrium. Now, why the molecule is affected by electromagnetic radiation? How is it affected by electromagnetic radiation? So electromagnetic means there is an electric field, there is a magnetic field, and there is a plane wave, not electron, but plane wave of electromagnetic light, right? So it oscillates in space and time. And when it hits the molecule, magnetic interaction is interesting but negligible. It's like 100 times smaller than electric. And electric, there is an electric field affects the molecule that has dipole, right? It's like in polar solids. And sometimes one needs to speak separately about static dipole for polar solids and transition dipole, special type of dipole that affects optical transitions. So basically, it is strength of electric field and strength of electric field times value of a dipole. So this dipole approximation, this dipole interaction, is explanation why molecules interact with light, with electromagnetic radiation. Now let's travel further. So it is dipole is amount of positive charge, amount of negative charge, and distance between them. If there is multiple charges, then it is arithmetic mean of all of them. Summations, and one needs to put denominator. So average position of all electrons with minus average position of all ions with plus. And Zion is not Zion, it is charge number of ion. Number ion. So it can be done if there are many things. And this transition operator, the light of frequency omega, transfers system from ground to excited. Make sense? Okay. So we are traveling further through this story. So the bridge between calculations and real world is a sandwich. So if you need an observable that theorists compute by pen and paper computers and experimenters and measurements with instruments, if they need to compare the results on the theory side, one needs to make a sandwich. Take wave function with star, wave function without star, and put in between the sandwich the operator of transition, operator of the which expectation value we need to find. So if you need to evaluate how happily system converts from ground to excited under light, we need to compose a sandwich of this dipole interaction operator, and then initial and final state with and without star. The state that includes both electronic and nuclear degree of freedom. Right? So I'm not contradicting to myself and to all exercises that we did in class. Next. The same thing. Initial, final, dipole interaction, dipole moment. And as soon as this matrix element has been found, one can find the rate of transitions. Like if we constantly radiate the system with light of certain frequency, how quickly the system will convert from ground to the excited state. This is computed by so-called Fermi's golden rule. So Enrico Fermi, like there is an element in periodic table, Fermi. He originally from Italy, moved to the States and contributed to making the first nuclear reactor and atomic bomb. So in very complicated situations, scientific problems, he offered a shortcut. Therefore, it is named after him. So a shortcut is how to get the transition rate out of matrix element. So it is this matrix element, which we call sandwich, squared, multiplied by density of final states, if there is more than one similar state as final. So if, and the brief take-home message that we shouldn't be happy with just taking the matrix element. We will need to take it squared, right? This is ugly. I was trying to type something. Yeah. So the goal is to take matrix element, evaluate it squared, but this will give the intensity of transitions. Right? In addition to intensity, we need transition energies. So how do we get transition energies? We need to take energy of the initial state and final state and subtract them. So the initial state is parabola with states 0, 1 to 3, upper state from 1 to 3, and the energy of each state can be set as the electronic energy of the ground plus 1/2 h bar omega, the zero phonon energy, plus quantum number for oscillations times h bar omega. And here I suggest we use upper cases for nuclei and lower cases for electrons. So if you do it for both ground and excited, then the upper state, generally for any transitions, even more than two, electronic state number m, lowercase, plus h bar omega vibrational, 1/2 plus m, quantum number for vibrations. Then lower states, electronic state n, with this epsilon plus h bar omega, 1/2 plus n. And if we subtract them, it will be subtraction of the electronic energy, which will refer to LUMO minus HOMO, plus subtraction of the quantum numbers for initial and final vibrational states. So this line will be an argument, will be define the frequency depending on which we set up the spectrum. And then each of these transition energies, we need intensities to get the image that we were discussing at the very beginning. So this energy goes into equation in here that I'm going to highlight. And this equation, which is highlighted, is implementation of Fermi's golden rule for towards spectroscopy. So if it needs to evaluate intensity of a line, which corresponds to rate of transition from ground to excited, as function of incident frequency omega, there will be matrix elements squared according to Fermi's golden rule, and instead of in place of density of states, we'll have this delta function, which means resonance. Right? It will be maximal if things under brackets coincide. And here we have frequency of the incident light and difference of frequencies between initial and ground state. So transitions will happen if the light is in resonance with nature of transitions at the moment. Before we met today, I may have thought that this resonance will be available only when light is in resonance with HOMO to LUMO energies. But in contrast to it, the best absorption will be at a little higher energy. There is so this resonance will be achieved at several values of initial and final vibrational states. Make sense? Let's stop for a second and check if there are questions in class or online. Spencer, Connor, Kennedy, if you have any objections or questions about statements before, let me know, because I will try to roll on more math and even more boring or more complicated. Okay, there you go. Checking, no questions online. Going forward with further sharing. Okay. So we know what to put as an argument, and now we need to evaluate the matrix element. Yes. I typed 2 slides this morning in addition to previous things. So maybe like the first thing to remember in years from now is the initial image with 2 parabolas and states. Second thing, which is optional to remember, but is kind of worth it, is this equation. So, and it is possible to remember. It's not as, even though it looks a little long, it is quite doable. So this is matrix element of transition from the state G naught to state E M. So according to our sandwich rule, we do have wave function for E naught in its cat form on the right, and we have wave function and we have excited comma M on the left, and in between we do have an operator. So based on Born-Oppenheimer approximation, we are separating variables. We represent this common vibration, means vibrational and electronic wave function, as a product of pure electronic wave function and pure nuclear wave function. So pure electronic, it can be clouds of orbitals in space, or we can describe it in discrete space as we did for spin. And just waveforms in this scheme. For vibrational part, it will be eigenstates of harmonic oscillator, but they are shifted according to equilibrium of this bond. So they're sent in different places. So we do have two types of eigenstates of harmonic oscillator at the left and right. So the indices are here, and I did a little poor job. One needs to specify that this is high excited and this is high ground, because these sets of eigenstates of harmonic oscillator are different for excited and ground. So to complete the practice of sandwich, one needs to integrate over electronic degrees of freedom and over nuclear degrees of freedom. What is inside? Inside there should be an operator of interaction. Dipole, which is charge times distance, times electric field, scalar product. Interestingly, if nucleus do not substantially move, one can leave the nuclear part from this dipole, but still the interaction operator must act on nuclear degrees of freedom. Like if we have at least two variables on the left and right, and we integrate over them, the operator also must depend on nuclear degrees of freedom. The simplest way of operator is simplest way of operator or simplest form of a matrix. Just give me a hint. It is not related to today's class. Like if you have 2 by 2 matrix and we need to fill it with numbers, what are the simplest ways?
Zeros.
Zeros, like trivial matrix, and what the second simplest?
Identity.
Or identity or
yes,
diagonal?
Identity. When we have ones on main diagonal and zeros elsewhere. Thank you. We are on the same page.
They're the same thing. You said it at the same time.
So we can define identity operator, which will act on the nuclear degrees of freedom, and basically it will be this 1111000 in the space of this nuclear wave function. So basically, we assume that this operator does not change the index of the nuclear quantum state. And if we put this operator here, just symbolically abstract, then it is a complete reasonable sandwich. Now, the most elegant thing that is a fundamental of the whole theoretical spectroscopy. So there will be a few more slides, but the transition from this one that you may remember to the next one will be very simple and elegant. So I'm going to reshuffle, reorder objects in this equation. I'm going to repeat the same equation, but in different order. So since we do not have any commutation problems in this operator, since electronic and nuclear functions are assumed to be independent of each other, I'm going to take everything that relates to electronic integration to the left, everything that relates to nuclear to the right, and compose a product. So integration over electronic degrees of freedom, wave function of electron, this dipole thing, and this wave function of electron in the ground. Then I'm going to make the second integration and use wave function of nuclear in the excited state, identity operator, wave function of nuclear in the ground state. So focus, focus. Here it is. Electronic, nuclear. Nuclear, not in the sense of nuclear bomb, nuclear in the sense of ions, nucleus. So now it is something that we can do without computer, if we need to. Of course, we are not going to do many computations now. So electronic, ground, excited, matrix element. And this, if you have only two electronic states, it will be a number. Just one number that you can compute or employ someone to compute it for us. Then what about this one? Identity operator can be placed or removed anywhere, right? So you can basically remove it and then take integral over R, which is index, and then we have a scalar product of the eigens oscillator eigenstate in the excited parabola number M, eigenstate oscillator in the ground number 0. If you remember where we started, there I have highlighted with black ground with a single hump and excited with 3 humps, right? So this is their overlap. And this overlap will be specific for each number M, and it is called FCF, Franck-Condon factor. Now I'm taking a marathon to complete. So do the same thing. We practice it. We go forward, and then there is a trick which I do not have time to focus on, but through our experience about harmonic oscillator, we know that eigenstate of harmonic oscillator can be represented as ground state and then creation operator acted on it several times, right? On another hand, we know that there is a so-called coherent state which has the same shape as ground state of the oscillator, but it is shifted elsewhere, right? Depending on this parameter eigenvalue of integration rate. So the trick is that if we are going to sit in the basis of excited state, then we can represent wave function of a ground state. To complicate, I'm going to blow up my mind. So we express, I need to draw. So we can express ground state of the ground vibrational ground electronic in terms of eigenstates of excited vibrational states. But in the basis of these vibrational states, it will be equivalent to a coherent state which is shifted from equilibrium. And if you do this trick, then one can, so if you play the stuff that we did when we studied coherent states, then one can find Franck-Condon factors without computers, with quite quick elementary math, well, that is possible to do in the remaining 7 minutes. So here is Franck-Condon factor from 0 state in ground to state M in the excited. So chi with index G, chi index E, number 0, number M. And here should be M. Now, if we consider things in the basis of excited state, then the ground state is superposition of all possible excited oscillator eigenfunctions with factors that come from the coherent state expansion. And it is this parameter of displacement, square root of number of eigenstates. So if we carefully process this matrix element, we can plug it into the Fermi's golden rule for absorption and basically get the profile, how the absorption spectrum should look if one does an experiment for the same mode. Questions? So I didn't. You're not lost yet. 5 minutes. So if one further processes this matrix element, then states from excited basis will cancel, and we will have only the expansion from the coherent state formula, only for the state M. Because in the excited state, all eigenstates do obey orthonormality. So as usual, we will remove wave functions and keep only numbers. And this number will come into the formula for the spectrum. So here are typical values. Just to do an example, so if it is something carbonaceous, then one needs to take 12 masses of proton and about so much in atomic units. The frequency is like 1/10 of electron volt. It's reasonable for vibrational frequency. The elongation, I just took this number, but it's like fraction of an angstrom and fraction of atomic unit. And then the parameter for displacement will be plugging these numbers into an equation that connects annihilation operator and displacement. So delta R frequency, mass, and Planck constant. So here's about 2. Well, basically, I took this number to get to here. Now, if it would be more time, we would invite all class attendees to the board and practice it. But here I'll do it myself. So, intensity of spectrum is electronic part times Franck-Condon factor squared, which is this E minus alpha squared power M divided by M factorial. So if you take square, the square disappears. Right? And then this intensity is function of the number. So if you plug values 0, 1, 2, 3, you will see trends. So the power wants this number to grow with M. The M factorial in the denominator will make it lower. So, and here one can put in the energy offsets so that when we do this X and Y, we will obtain the spectrum. So, e to the minus 4 close to 0, e to the, no, not 0, bigger. But carefully just plugging in, there should be, yes, there should be numbers. So e to the power minus 4 and then multiplied by the numbers 1, 4, 8, 10.6, 8, 6, 3.26. So you see the trend, it increases, decreases. And energy goes here as the integer of fundamental frequency. Now, if you plug in these numbers into the dependence and assign a little Gaussian profile as we did for density of states, we will get the wing of an eagle, the spectrum of absorption, right? So several peaks. And here, I'm not yet done, I'm going to show something more. Here is the image we started from, right? And here is the arrow show lowest possible transition, right? Then here is the second possible transition. It becomes more intense. Here is the one, the most intense because of the best overlap between green and red wave functions. And then you get less overlap and it starts decreasing. There. So, one. Thank you for your questions. Wishing you to successfully complete the remaining part of the class, which means the project report and then presentation. And I will be happy to answer any questions by emails or personally if you come up